The windows shattered for miles around, not from bombs, not from explosions, but from the thunderous roar of 10 engines screaming through the sky. This was the Convair B-36 Peacemaker, a machine so massive that mechanics could walk upright inside its wings during flight, a flying fortress so enormous that its shadow could eclipse entire city blocks. And yet, this aluminum leviathan was destined to become one of history's most spectacular technological dead ends. Welcome to Never Built, where we explore the magnificent failures that shaped our world. I'm your host, and today we're diving deep into the story of the largest piston-engine bomber ever built, a machine that was supposed to secure America's nuclear supremacy, but instead became the last gasp of a dying era. Before we take off on this incredible journey, make sure to subscribe to Never Built and hit that notification bell. And I want to hear from you. Drop a comment below and tell me, what's the most ambitious project you think should have succeeded? Let's get this conversation started. Picture this. It's the late 1940s, and the world has just witnessed the devastating power of atomic weapons. The United States needs a way to deliver these massive early nuclear bombs anywhere on Earth. But there's a problem. No aircraft exists that can carry a 10,000-pound atomic bomb across the Atlantic Ocean and back. Enter the Convair B-36, a machine so audacious in its design that it defied every convention of aviation engineering. This wasn't just another bomber. This was a flying city. With a wingspan of 230 feet, wider than a football field is long, the B-36 was a testament to American industrial might and engineering ambition. Its 6 massive Pratt and Whitney R-4360 engines, each producing 3,500 horsepower, were supplemented by 4 additional jet engines mounted under the wings, 10 engines total, earning it the nickname 6 turning and 4 burning. But here's what makes this story truly fascinating. The B-36 was obsolete before it ever reached full operational status. By the time this mechanical marvel was patrolling the skies, intercontinental ballistic missiles were already being developed. The age of the strategic bomber was ending just as its greatest achievement was taking flight. Today, we're going to explore how the B-36 Peacemaker became both a triumph of engineering and a symbol of technological transition. We'll uncover the desperate circumstances that led to its creation, the incredible challenges faced by its designers, and the human stories of the crews who flew these aluminum giants through 40-hour missions that pushed both man and machine to their absolute limits. What do you think? Was the B-36 a necessary bridge between propeller and jet age, or was it pure technological ambition flying in the face of reality? Let me know in the comments below. The year was 1941, and America was staring into the abyss of global warfare. Pearl Harbor had just been attacked, and military planners were facing a terrifying reality. If Britain fell to Nazi Germany, the United States would need to bomb Europe from bases in North America. The problem? No aircraft in existence could make that journey while carrying a meaningful bomb load. Enter the visionaries at Consolidated Aircraft Corporation, later known as Convair. Led by Chief Engineer Isaac M. Ladden, the team was tasked with creating something that had never existed before, a truly intercontinental bomber. The specifications were staggering. The aircraft needed to carry a 10,000-pound bomb load over a distance of 5,000 miles and return to base without refueling. To put this in perspective, the famous B-17 Flying Fortress had a combat range of just 2,000 miles with a 4,000-pound bomb load. What the military was asking for was more than double the range with more than double the payload. It was, by any measure of 1940s technology, impossible. But Ladden and his team weren't deterred by impossibility. They began with a radical premise. If you can't make existing technology work, you have to invent new technology. The result was a design so ambitious that it challenged every assumption about aircraft construction. The initial concept called for a wingspan of 230 feet, so wide that the aircraft couldn't fit in any existing hangar. The fuselage would be over 160 feet long, making it longer than the Wright brothers' first flight. And the weight? When fully loaded, this monster would tip the scales at over 185,000 pounds. The engineering challenges were immediate and overwhelming. How do you build wings strong enough to support such massive weight? How do you create engines powerful enough to lift this giant off the ground? How do you even transport the components to an assembly facility? The solution lay in pushing every aspect of aircraft technology to its absolute limit. The wings would be so thick that they could house fuel tanks, landing gear, and even crew compartments. The engines would be the largest piston engines ever built for aircraft use, and the entire structure would need to be built using revolutionary new construction techniques. But perhaps the most audacious aspect of the design was its intended mission profile. This wasn't just a bomber. It was designed to be a flying fortress capable of defending itself against enemy fighters while carrying enough fuel to stay airborne for over 40 hours. The crew of 15 would need sleeping quarters, a galley, and even a relief crew to handle the marathon flights. The project, designated B-36, received official approval in November 1941, just weeks after Pearl Harbor. The contract called for 2 prototype aircraft at a cost of $15 million, equivalent to over $200 million today. It was one of the largest aircraft development contracts in history, and it was betting everything on technologies that didn't yet exist. Construction began in 1943 at Convair's facility in San Diego, California, but almost immediately the project ran into problems. The sheer scale of the aircraft meant that new manufacturing techniques had to be developed. Special tools had to be created, new materials had to be tested. Every component was pushing the boundaries of what was possible with 1940s technology. The wing construction alone was a marvel of engineering. Each wing was built in sections, with massive spars running the entire length. The wing was so thick at the root, over 7 feet, that engineers could literally walk through it during construction. Fuel tanks were integrated into the wing structure, giving the aircraft an unprecedented fuel capacity of over 21,000 gallons. But the real breakthrough came with the engine selection. Pratt & Whitney had been developing the R4360 Wasp Major, a massive 28-cylinder radial engine that produced 3,500 horsepower. It was the most powerful piston engine ever built for aircraft use, and the B-36 would need 6 of them. The engines were mounted in a pusher configuration, meaning the propellers pushed rather than pulled the aircraft through the air. This was done for several reasons. It kept the propeller wash away from the fuselage. It allowed for better engine cooling, and it provided some protection for the engines from enemy fire. Each engine drove a massive 19-foot diameter propeller, so large that ground crews needed special equipment just to start them. The sound of 6 of these engines at full power was unlike anything ever heard before. Test pilots described it as the sound of the world ending. By 1945, as World War II was ending, the first B-36 was nearing completion. But the world had changed dramatically. The atomic bomb had been developed and used, fundamentally altering the nature of strategic warfare. Suddenly, the mission of the B-36 wasn't just about carrying conventional bombs across oceans, it was about delivering nuclear weapons. This shift in mission requirements would prove to be both a blessing and a curse for the B-36 program. On one hand, it provided renewed justification for the enormous expense and complexity of the aircraft. On the other hand, it meant that the B-36 would need to be capable of carrying weapons that were still being developed, with specifications that were constantly changing. The first flight of the B-36 finally took place on August 8, 1946, from Carswell Air Force Base in Texas. Test pilot Beryl Erickson later described the experience as like trying to fly a city block. The aircraft performed reasonably well, but it was clear that significant modifications would be needed before it could enter operational service. What emerged from those early test flights was both encouraging and concerning. The B-36 could indeed fly, and it could carry enormous loads over vast distances. But it was also clear that this was a machine operating at the very edge of technological possibility. Every flight was an adventure, every mission a test of both human endurance and mechanical reliability. The birth of the B-36 represents one of those pivotal moments in technological history where ambition meets necessity. But was it visionary engineering or technological hubris? What do you think drove these engineers to attempt the impossible? Share your thoughts in the comments. Imagine trying to build a flying machine the size of a city block using 1940s technology. No computers to calculate stress loads, no advanced materials, no sophisticated manufacturing techniques. Just slide rules, wind tunnels, and the accumulated wisdom of engineers who were literally making it up as they went along. This was the reality facing the Convair engineering team as they attempted to turn the B-36 from concept to reality. The first major challenge was the wing structure. At 230 feet from tip to tip, the B-36's wing was larger than the entire fuselage of most contemporary aircraft. The wing had to support not just the weight of the aircraft, but also the massive engines, fuel tanks, landing gear, and bomb load. The total wing loading would be unprecedented in aviation history. Chief Engineer Isaac Ladden and his team developed a revolutionary wing design that was essentially a flying fuel tank. The wing was built around massive aluminum spars that ran from root to tip, creating a structure so strong that it could support the entire weight of the aircraft on just the wingtips during certain maneuvers. But strength came at a cost. The wing alone weighed over 30,000 pounds empty. The wing's internal structure was a maze of fuel tanks, wiring, hydraulic lines, and access tunnels. Engineers could literally crawl through the wing during maintenance, accessing engines, fuel systems, and other components. This wasn't just convenient, it was necessary. The B-36 was so large that external maintenance would have been nearly impossible for many components. But the wing presented another unprecedented challenge. How do you test a structure this large? Traditional wind tunnel testing was impossible. No wind tunnel in the world was large enough to accommodate even a scale model of the complete aircraft. Instead, engineers had to test individual components and use complex mathematical calculations to predict how they would behave when assembled. The engine installation presented its own set of seemingly impossible challenges. Each Pratt & Whitney R4360 Wasp major engine was a mechanical marvel in its own right. With 28 cylinders arranged in 4 rows of 7, these engines were the most complex piston engines ever built for aircraft use. They produced 3,500 horsepower each, but they also generated enormous amounts of heat and vibration. Mounting 6 of these monsters in the wing required completely new engineering solutions. Each engine was housed in a nacelle that was essentially a small aircraft in itself, complete with cooling systems, fire suppression, and access panels. The engines were mounted in a pusher configuration with the propellers behind the wing, which created unique aerodynamic challenges. The propellers themselves were engineering marvels. At 19 feet in diameter, each propeller was larger than the entire engine of many contemporary aircraft. They were made of hollow steel blades filled with anti-icing fluid, and they could be feathered, turned edge-on to the airflow if an engine failed. The sound of 6 of these massive propellers spinning at full power was so loud that it could be heard from over 20 miles away. Cooling these massive engines presented another unprecedented challenge. Each R4360 generated enough heat to warm a small building, and all that heat had to be dissipated while the aircraft was flying at high altitude where the air was thin and cold. The solution was a complex system of cooling flaps, baffles, and ducting that could be adjusted in flight to maintain optimal engine temperatures. The fuel system was perhaps the most complex ever installed in an aircraft. With over 21,000 gallons of fuel distributed throughout the wing and fuselage, The B-36 required an intricate network of pumps, valves, and monitoring systems to ensure proper fuel distribution. The fuel had to be carefully balanced to maintain the aircraft's center of gravity as it was consumed during flight. But fuel wasn't the only liquid system that required engineering innovation. The B-36 also carried hydraulic fluid for the flight controls, oil for the engines, and various other fluids for different systems. All of these had to be routed through the aircraft in a way that minimized weight while maximizing reliability. A single hydraulic failure could render the aircraft uncontrollable. The electrical system was equally complex. The B-36 required enough electrical power to supply a small town, and all of that power had to be generated by engine-driven generators while maintaining redundancy in case of engine failure. Miles of wiring snaked through the aircraft, connecting everything from navigation equipment to bomb bay doors. Perhaps the most challenging aspect of the B-36's engineering was the landing gear. How do you design landing gear capable of supporting 185,000 pounds while still being light enough for flight? The solution was a complex system of multiple wheels and shock absorbers that retracted into the wing and fuselage. The main landing gear consisted of four-wheel bogies that retracted into the wing, while the nose gear was a single wheel that retracted forward into the fuselage. The gear had to be strong enough to handle the massive weight during landing, yet reliable enough to retract and extend thousands of times over the aircraft's service life. Ground handling presented its own unique challenges. The B-36 was too large for most existing hangars and too heavy for most runways. Special facilities had to be built at bases that would operate the aircraft, including reinforced runways, oversized hangars, and specialized ground support equipment. The flight control system required completely new approaches to aircraft design. Traditional cable and pulley systems wouldn't work on an aircraft this large. The control forces would be too great for human pilots to handle. Instead, the B-36 used a complex system of hydraulically boosted controls that gave pilots the mechanical advantage needed to control the massive aircraft. But hydraulic boost created its own problems. What happens if the hydraulic system fails? The solution was multiple redundant systems, but even with backups, flying the B-36 required constant attention to system status. Pilots had to monitor dozens of gauges and indicators, watching for signs of impending system failures. The pressurization system was another engineering challenge. To fly at the high altitudes necessary for its mission, the B-36 needed a pressurized crew compartment. But pressurizing such a large volume required powerful compressors and a structure strong enough to withstand the pressure differential. The engineering team had to essentially build a pressure vessel that could also fly. Testing all of these systems required new approaches to aircraft development. Traditional flight testing involved a few dozen flights over several months. The B-36 required hundreds of test flights over several years, with each flight revealing new problems that needed to be solved. Engineers were literally learning how to build and operate such a massive aircraft as they went along. The manufacturing process itself required revolutionary new techniques. The aircraft was too large to be built in a traditional factory, so Convair had to develop new assembly methods that could handle components of unprecedented size and weight. Special cranes, jigs, and tooling had to be created just for the B-36 program. Quality control was another massive challenge, with millions of individual parts and components. Ensuring that everything was built to specification required new inspection techniques and documentation systems. A single faulty rivet or improperly installed wire could potentially cause a catastrophic failure. By the time the first production B-36A rolled out of the factory in 1948, it represented the culmination of one of the most ambitious engineering projects in aviation history. But it also represented something else: the absolute limit of piston engine technology. Every system, every component, every design element was pushed to its maximum capability. The engineering challenges of the B-36 were so extreme that they pushed 1940s technology beyond its limits. Do you think this kind of extreme engineering is still possible today, or have we become too risk-averse? What's your take on pushing technology to its absolute limits? Let me know in the comments. By 1948, it was becoming clear that the B-36, despite its massive size and power, had a critical weakness. It was too slow. The 6 Pratt & Whitney R4360 engines, massive as they were, could only push the aluminum giant to a maximum speed of about 400 miles per hour. In an era where jet fighters were beginning to exceed the speed of sound, this made the B-36 a sitting duck for enemy interceptors. The solution was as audacious as the original design. Add jet engines. Not as replacements for the piston engines, but as supplements. The result would be a hybrid propulsion system, unlike anything ever attempted. 6 massive piston engines for long-range cruise efficiency, plus 4 jet engines for high-speed dash capability and improved takeoff performance. This decision transformed the B-36 from an already complex aircraft into something approaching technological madness. Imagine the engineering challenges. You now had 2 completely different propulsion systems that had to work together seamlessly. Different fuel types, different operating characteristics, different maintenance requirements, all integrated into a single aircraft. The jet engines chosen were General Electric J-47S, the same engines that powered the F-86 Sabre fighter. Each engine produced 5,200 pounds of thrust, and 4 of them were mounted in pairs under the outer wing sections. This gave the modified B-36 a total of 10 engines, 6 piston and 4 jet, earning it the nickname 6 turning and 4 burning. But adding jet engines to a piston-powered aircraft created unprecedented challenges. The jets burned a different type of fuel, JP4 jet fuel, instead of aviation gasoline. This meant the aircraft now needed 2 separate fuel systems with different pumps, lines, and storage tanks. The complexity of the fuel management system increased exponentially. The jet engines also operated at much higher temperatures than the piston engines. While the R436 ran hot by piston engine standards, the J47s operated at temperatures that could literally melt aluminum. Special heat shields and cooling systems had to be designed to protect the wing structure from the intense heat of the jet exhausts. The electrical demands of the hybrid system were staggering. The piston engines required one type of ignition system, while the jets required completely different electrical systems for starting an operation. The aircraft's electrical generation capacity had to be increased dramatically to handle the additional load. Perhaps most challenging was integrating the 2 propulsion systems operationally. The piston engines were most efficient at lower altitudes and speeds, while the jets were designed for high-altitude, high-speed operation. Pilots had to learn to manage both systems simultaneously, balancing fuel consumption, power output, and operational efficiency across 10 different engines. The startup procedure alone became a complex choreographed dance. The piston engines had to be started first, using external power carts and ground crews. Each R4360 required a careful warm-up procedure that could take 30 minutes or more. Only after all 6 piston engines were running and warmed up could the jets be started, using power generated by the piston engines. In flight, the jet engines were typically used only for takeoff, high-speed dashes, or when maximum performance was required. During normal cruise flight, the jets were shut down to conserve fuel, and the aircraft operated on piston power alone. But the ability to light off those 4 jets gave the B-36 a performance boost that could mean the difference between life and death in combat. The sound of a B-36 with all 10 engines running was unlike anything ever heard before or since. The deep, rhythmic throb of the 6 massive piston engines was overlaid with the high-pitched scream of 4 jet engines. People on the ground described it as the sound of the apocalypse, a mechanical roar so loud and distinctive that it could be identified from dozens of miles away. Maintenance of the hybrid system was a nightmare of complexity. Ground crews had to be trained on 2 completely different types of engines, each with their own specialized tools, procedures, and spare parts. A typical engine change on a B-36 could take days, and that was assuming the right parts and equipment were available. The jet engines, being much newer technology, were particularly problematic. The J-47s were reliable by jet engine standards of the time, but those standards were far below what was acceptable for piston engines. Jet engine failures were common, and the engines had much shorter service lives than their piston counterparts. Fuel consumption became a critical factor in mission planning. The piston engines, while thirsty, were relatively efficient for their power output. The jets, however, consumed fuel at a prodigious rate. With all 10 engines running, a B-36 could burn through its entire fuel load in just a few hours. This meant that jet power had to be used sparingly and strategically. The hybrid configuration also created unique flight characteristics. With only the piston engines running, the B-36 flew like a very large, very heavy conventional aircraft. But when the jets were lit, the aircraft's performance changed dramatically. Acceleration increased, climb rate improved, and maximum speed jumped by over 100 miles per hour. Pilots had to learn to manage these different flight regimes carefully. The transition from piston-only to hybrid power had to be smooth and coordinated to avoid dangerous flight attitudes or structural stress. Similarly, shutting down the jets in flight required careful attention to power settings and aircraft balance. The weight penalty of the hybrid system was significant. The 4 jet engines, their fuel systems, and associated equipment added thousands of pounds to an aircraft that was already pushing the limits of structural capability. This additional weight reduced the aircraft's range and payload capacity, partially negating the benefits of the improved performance. Despite these challenges, the hybrid B-36 represented a remarkable achievement in aviation engineering. It was a machine that bridged 2 eras of aviation technology: the age of piston engines and the dawning jet age. For a brief period in the early 1950s, it was the most powerful aircraft in the world, capable of delivering nuclear weapons anywhere on the planet. But the hybrid configuration also highlighted the fundamental problem with the B-36 concept. It was a machine caught between 2 technological paradigms, trying to combine the best of both worlds, but inevitably compromised by the complexity of doing so. The future belonged to pure jet aircraft, and the B-36's hybrid system was ultimately a technological dead end. The operational reality of flying 10 engines simultaneously was daunting. Engine failures were not uncommon, and losing engines during flight created complex emergency procedures. Pilots had to be prepared to handle failures in either propulsion system while maintaining control of the massive aircraft. Training pilots for the B-36 became a major undertaking in itself. The aircraft was so unique that there was no comparable training aircraft. Pilots had to learn on the actual B-36, starting with extensive ground school and simulator training before progressing to actual flight training. The learning curve was steep, and the consequences of mistakes could be catastrophic. The hybrid B-36 flew operational missions for nearly a decade, serving as America's primary strategic bomber during the early years of the Cold War. But even as it was performing its mission, newer, faster, more capable jet bombers were being developed. The writing was on the wall. The age of the hybrid giant was coming to an end. The B-36's hybrid propulsion system was either brilliant engineering or technological desperation. Maybe both. In today's world of electric hybrid vehicles, are we repeating the same pattern of bridging old and new technologies? What parallels do you see between the B-36's hybrid system and modern technological transitions? Share your thoughts below. The B-36 wasn't just designed to carry bombs, it was specifically engineered to carry the most destructive weapons ever created by humanity. When the first atomic bombs were dropped on Japan in 1945, they weighed over 9,000 pounds each and required specially modified B-29 superfortresses to carry them. The early nuclear weapons were massive, crude devices that pushed the limits of aircraft payload capacity. By the time the B-36 entered service, nuclear weapons had evolved into even more powerful and sophisticated devices. The hydrogen bombs of the early 1950s could weigh up to 25,000 pounds, more than the entire bomb load capacity of most World War II bombers. The B-36 was one of the few aircraft in the world capable of carrying these weapons of mass destruction. The bomb bay of the B-36 was a cavernous space, over 28 feet long, 6 feet wide, and nearly 7 feet high. It could accommodate a single massive thermonuclear weapon or multiple smaller nuclear devices. Special handling equipment was required to load these weapons, as their weight and radioactive nature made them extremely dangerous to work with. But carrying nuclear weapons created unique challenges that went far beyond simple weight and size considerations. The weapons themselves were highly sensitive to temperature, vibration, and electromagnetic interference. The B-36 had to be equipped with specialized environmental control systems to maintain the weapons at precise temperatures during long flights. The electrical systems of the aircraft had to be carefully shielded to prevent electromagnetic interference from affecting the weapon's electronic components. A stray electrical signal could potentially cause a malfunction in the weapon's arming system, with catastrophic consequences for the aircraft and crew. Security considerations for nuclear-armed B-36 were unprecedented. These aircraft carried weapons capable of destroying entire cities, making them high-value targets for enemy intelligence services and saboteurs. Special security protocols were developed for nuclear-armed missions, including armed guards, restricted access areas, and coded communication procedures. The crew training for nuclear missions was extensive and highly classified. Pilots and bombardiers had to learn not just how to deliver nuclear weapons, but how to survive the effects of their own weapons. The thermal flash from a nuclear explosion could blind aircrew from dozens of miles away, while the electromagnetic pulse could disable electronic systems. Special procedures were developed for nuclear weapon delivery. Unlike conventional bombing, where accuracy was measured in hundreds of feet, nuclear weapons were so powerful that they could destroy their targets even with relatively poor accuracy. But this also meant that the delivering aircraft had to escape the blast zone quickly to avoid being destroyed by its own weapon. The B-36's size and endurance made it ideal for nuclear deterrent missions. During the height of the Cold War, B-36s would take off from bases in the United States and fly to the edge of Soviet airspace, demonstrating America's ability to deliver nuclear weapons anywhere in the world. These show-of-force missions could last over 20 hours and cover thousands of miles. But the aircraft's nuclear mission also made it a target. Soviet fighter aircraft and surface-to-air missiles were specifically designed to intercept and destroy American strategic bombers. The B-36's defensive armament, 1650 caliber machine guns and remote-controlled turrets, was formidable, but ultimately inadequate against modern jet fighters. The psychological impact of the B-36's nuclear capability cannot be overstated. This was an aircraft that could single-handedly destroy entire nations. The knowledge that dozens of these aircraft were constantly on alert, ready to launch nuclear strikes at a moment's notice, fundamentally changed the nature of international relations. The aircraft's crew compartments were designed with nuclear warfare in mind. The pressurized crew areas provided some protection against radioactive fallout, while special filters could remove radioactive particles from the air supply. But these measures were largely psychological. In reality, a nuclear exchange would likely be fatal for everyone involved. Navigation for nuclear missions required unprecedented precision. The B-36's navigation systems included celestial navigation equipment, radar, and early electronic navigation aids. Navigators had to be capable of finding targets thousands of miles away with accuracy measured in miles, not the hundreds of miles that were acceptable for conventional bombing. Communication systems were equally critical. Nuclear-armed B-36 had to maintain constant contact with command authorities, ready to receive launch orders or recall commands. The aircraft were equipped with multiple radio systems operating on different frequencies to ensure communication could be maintained even in the face of enemy jamming. The fuel requirements for nuclear missions were staggering. A typical nuclear strike mission could require the B-36 to fly over 8,000 miles without refueling. This meant taking off with maximum fuel load, which in turn meant reduced payload capacity. Mission planners had to carefully balance fuel requirements against weapon load and target priorities. Weather considerations were critical for nuclear missions. Unlike conventional bombing, where missions could be postponed due to weather, nuclear strike missions might need to be executed regardless of conditions. The B-36 was equipped with weather radar and other meteorological equipment to help crews navigate through storms and adverse conditions. The maintenance requirements for nuclear-capable B-36s were extraordinary. Every system had to be maintained to the highest possible standards, as equipment failure during a nuclear mission could have global consequences. Special maintenance procedures were developed for aircraft that had been exposed to radioactive materials. Ground support for nuclear missions required specialized equipment and personnel. Loading nuclear weapons required specially trained technicians using specialized handling equipment. The weapons themselves were stored in heavily guarded bunkers with elaborate security systems to prevent unauthorized access. The human cost of operating nuclear-armed B-36 was significant. Aircrew members were constantly aware that they were training to potentially end civilization as we know it. The psychological stress of this responsibility, combined with the physical demands of flying such a complex aircraft, took a heavy toll on personnel. Despite never being used in anger, the B-36's nuclear capability served its intended purpose as a deterrent. The knowledge that America possessed aircraft capable of delivering nuclear weapons anywhere in the world helped maintain the balance of terror that characterized the early Cold War period. But the B-36's role as a nuclear delivery system also highlighted its fundamental vulnerability. As Soviet air defenses improved and jet fighters became faster and more capable, it became increasingly clear that large, slow bombers like the B-36 would not survive in a nuclear war environment. The development of intercontinental ballistic missiles in the late 1950s provided a more survivable means of nuclear weapon delivery. ICBMs could reach their targets in minutes rather than hours, and they were virtually impossible to intercept with existing technology. The age of the strategic bomber as the primary nuclear delivery system was coming to an end. The B-36 represented the peak of manned nuclear delivery systems, but it also showed the limitations of that approach. Today we're seeing similar debates about manned versus unmanned systems in military technology. Do you think human crews will always have a role in strategic weapon systems, or is the future entirely automated? What are your thoughts on the human element in weapons of mass destruction? Imagine being locked inside an aluminum tube with 14 other people for 40 hours straight, flying at 35,000 feet over hostile territory, knowing that enemy fighters could appear at any moment and that you're carrying enough nuclear firepower to level a major city. This was the reality for B-36 aircrew members during the height of the Cold War. The human challenges of operating the B-36 were as daunting as the technical ones. A typical strategic reconnaissance mission could last over 40 hours, pushing both aircraft and crew to their absolute limits. These weren't just long flights. They were endurance tests that demanded peak performance from every crew member for nearly 2 full days. The crew complement of a B-36 varied depending on the mission, but typically included 15 highly trained specialists: pilot, co-pilot, flight engineer, navigator, bombardier, radio operator, radar operator, and 8 gunners to operate the defensive armament. Each crew member had specific responsibilities that were critical to mission success and crew survival. Living conditions aboard the B-36 during these marathon flights were Spartan at best. The pressurized crew compartment provided basic life support, but comfort was not a priority. Crew members had to sleep in shifts on narrow bunks, eat cold meals from ration packs, and deal with the constant noise and vibration of 10 engines running at cruise power. The physical demands of flying the B-36 were enormous. The aircraft's controls were heavy and required constant attention. Even with hydraulic boost, flying the massive bomber was exhausting work. Pilots and co-pilots had to alternate control duties every few hours to prevent fatigue from compromising flight safety. Navigation on 40-hour missions required extraordinary skill and precision. Before the advent of satellite navigation, navigators relied on celestial navigation, radio beacons, and dead reckoning to find their way across thousands of miles of ocean and hostile territory. A navigation error of just a few degrees could put the aircraft hundreds of miles off course. The psychological stress of B-36 operations cannot be overstated. Crew members were constantly aware that they were flying one of the most valuable and vulnerable aircraft in the world. Enemy fighters, surface-to-air missiles, and mechanical failures were constant threats. The knowledge that capture would likely mean torture and execution added another layer of stress. Communication during long missions was critical, but challenging. Radio operators had to maintain contact with command authorities across vast distances, often dealing with atmospheric interference, enemy jamming, and equipment failures. The ability to receive updated orders or weather information could mean the difference between mission success and disaster. Engine management during 40-hour flights was a constant challenge. The flight engineer had to monitor dozens of engine parameters, watching for signs of impending failure. Engine failures were not uncommon, and losing engines during flight over hostile territory created life-threatening emergencies. The defensive systems of the B-36 required constant vigilance from the gunners. The aircraft's 1650 caliber machine guns were controlled remotely from gunner stations throughout the aircraft. Gunners had to be ready to engage enemy fighters at a moment's notice, often while dealing with the disorientation of high-altitude flight. Medical emergencies during 40-hour flights presented unique challenges. The aircraft carried basic medical supplies, but serious injuries or illnesses could not be treated adequately at altitude. Emergency descents were dangerous and could compromise the mission, but they were sometimes necessary to save crew members' lives. Weather was a constant concern during long missions. B-36s had to fly through storms, icing conditions, and severe turbulence that could damage the aircraft or injure crew members. The aircraft's weather radar helped, but crews often had to make difficult decisions about whether to fly through dangerous weather or abort the mission. Fuel management during extended flights required constant attention. The flight engineer had to carefully monitor fuel consumption and transfer fuel between tanks to maintain proper aircraft balance. Running out of fuel over hostile territory was a death sentence, so fuel calculations had to be precise and conservative. The bombardier's role during nuclear missions carried enormous psychological weight. This crew member was responsible for arming and delivering weapons capable of killing hundreds of thousands of people. The training for nuclear weapon delivery included detailed instruction on the effects of nuclear weapons, knowledge that weighed heavily on those who possessed it. Sleep deprivation was a major factor during 40-hour missions. Crew members had to sleep in shifts, but the noise, vibration, and stress of flight made quality sleep nearly impossible. Fatigue-related errors became increasingly likely as missions progressed, creating additional safety hazards. The radar operator played a crucial role in detecting enemy aircraft and guiding the defensive response. The early radar systems of the 1950s were primitive by today's standards, requiring skilled interpretation to distinguish between genuine threats and false returns. A missed detection could be fatal for the entire crew. Emergency procedures for the B-36 were complex and had to be executed flawlessly under extreme stress. Crew members trained extensively for various emergency scenarios, from engine failures to pressurization loss to enemy attack. But no amount of training could fully prepare them for the reality of a life-threatening emergency at 35,000 feet over enemy territory. The physical environment inside the B-36 was harsh. Despite pressurization, the cabin altitude was equivalent to about 8,000 feet, causing fatigue and reducing mental acuity. Oxygen masks were available for higher altitudes, but wearing them for hours was uncomfortable and made communication difficult. Temperature control was another challenge. The aircraft's heating system struggled to keep the crew compartment warm at high altitude, while the heat from electronic equipment and engines could make some areas uncomfortably hot. Crew members had to dress in layers and be prepared for wide temperature variations. The social dynamics of spending 40 hours in close quarters with 14 other people created unique challenges. Personality conflicts, stress, and fatigue could lead to tensions that compromised crew effectiveness. Crew selection and training included psychological evaluation to identify individuals who could work effectively under these extreme conditions. Maintenance issues during flight were common and often dangerous. Crew members sometimes had to perform repairs while the aircraft was in flight, crawling through the wing tunnels to access engines or other systems. These repairs were often performed without proper tools or safety equipment in conditions that would be considered unacceptably dangerous today. The return journey was often the most dangerous part of a mission. Crew members were exhausted, fuel was low, and the aircraft had been operating at its limits for dozens of hours. Landing a B-36 after a 40-hour mission required extraordinary skill and concentration from pilots who were often at the edge of their physical and mental capabilities. The human cost of operating the B-36 was enormous, but these crews were willing to endure incredible hardships in service of their mission. In our modern world of automation and remote operations, do you think we've lost something important about human endurance and dedication? What can we learn from these Cold War air crews about pushing human limits? Let me know your thoughts. By the mid-1950s, the B-36 Peacemaker was at the height of its operational capability. Strategic Air Command had over 300 of these aluminum giants in service, capable of delivering nuclear destruction to any point on Earth. But even as these massive bombers patrolled the skies, the seeds of their obsolescence were already being planted in the laboratories and test facilities of America and the Soviet Union. The first hint of the B-36's impending doom came not from enemy action, but from technological advancement. On October 4, 1957, the Soviet Union launched Sputnik, the world's first artificial satellite. This basketball-sized sphere, orbiting Earth every 96 minutes, represented more than just a scientific achievement. It was proof that the Soviets had developed intercontinental ballistic missile technology. The implications were staggering. If the Soviets could put a satellite into orbit, they could deliver a nuclear warhead to any target on Earth in less than 30 minutes. Suddenly, the B-36's 40-hour mission profile seemed not just slow, but absurdly obsolete. Why spend 2 days flying a massive bomber across the ocean when you could deliver the same destructive payload in half an hour with a missile? The American response was swift and decisive. The Atlas Intercontinental Ballistic Missile Program, which had been proceeding at a relatively leisurely pace, was suddenly elevated to the highest national priority. Billions of dollars were redirected from bomber programs to missile development. The age of the strategic bomber was ending, and the missile age was beginning. But the technological obsolescence of the B-36 had been apparent to some observers even before Sputnik. The aircraft's fundamental design philosophy, massive size, long endurance, and heavy defensive armament, was based on World War II concepts of strategic bombing. The reality of nuclear warfare was fundamentally different from conventional bombing campaigns. Nuclear weapons were so powerful that accuracy was less critical than with conventional bombs. A nuclear weapon could destroy its target even if it missed by several miles. This meant that the precision bombing techniques that had been developed during World War II were largely irrelevant in the nuclear age. Speed and survivability became more important than accuracy and payload capacity. The Soviet development of high-altitude surface-to-air missiles posed another existential threat to the B-36. The SA-2 guideline missile system, first deployed in the mid-1950s, was specifically designed to intercept high-altitude bombers. With a maximum altitude of over 80,000 feet, the SA-2 could reach altitudes far higher than the B-36 could fly. Soviet jet fighters were also becoming increasingly capable of intercepting strategic bombers. The MiG-19 and later the MiG-21 were fast enough to catch a B-36 and heavily armed enough to destroy it. The B-36's defensive armament, formidable as it was, could not provide adequate protection against modern jet fighters attacking with air-to-air missiles. The economics of strategic deterrence were also changing. A single Atlas ICBM cost a fraction of what it cost to build, maintain, and operate a B-36. Missiles didn't require highly trained crews, extensive support facilities, or constant maintenance. They could be stored in underground silos for years, ready to launch at a moment's notice. The vulnerability of bomber bases became another critical factor. B-36s required massive runways, huge hangars, and extensive support facilities. These bases were easily identified by enemy reconnaissance and could be destroyed by a small number of nuclear weapons. Missile silos, by contrast, could be hardened against nuclear attack and dispersed over wide areas. The human factor also played a role in the B-36's obsolescence. Training and maintaining crews for 40-hour missions was extremely expensive and time-consuming. Crew fatigue and human error were constant concerns during long missions. Missiles eliminated the human element from strategic nuclear delivery, reducing the possibility of errors or hesitation at critical moments. The development of nuclear-powered submarines provided another alternative to strategic bombers. The USS Nautilus, launched in 1954, demonstrated that submarines could remain submerged for weeks at a time, making them nearly invulnerable to enemy attack. Submarine-launched ballistic missiles could deliver nuclear weapons from positions close to enemy coastlines, reducing flight time and increasing accuracy. The B-36's massive fuel consumption became a liability in an era of increasing cost consciousness. A single 40-hour mission could consume over 20,000 gallons of fuel, not counting the fuel burned by escort fighters and tanker aircraft. The operating costs of the B-36 fleet were enormous, consuming a significant portion of the defense budget. Maintenance requirements for the B-36 were also becoming increasingly burdensome. The aircraft's 10 engines required constant attention, and the complexity of its systems meant that maintenance crews needed extensive specialized training. As the aircraft aged, maintenance requirements increased while availability decreased. The changing nature of nuclear strategy also worked against the B-36. Early nuclear doctrine emphasized massive retaliation, the threat to respond to any aggression with overwhelming nuclear force. This strategy favored large numbers of strategic bombers capable of delivering massive payloads. But as nuclear arsenals grew and delivery systems became more sophisticated, strategy shifted toward more flexible response options. The development of tactical nuclear weapons reduced the importance of strategic bombers for some missions. Smaller nuclear weapons could be delivered by fighter bombers or short-range missiles, eliminating the need for intercontinental bombers for some targets. The B-36's massive size and long range were overkill for many potential missions. Intelligence gathering became increasingly important during the Cold War, and the B-36's size and slow speed made it poorly suited for reconnaissance missions over hostile territory. Smaller, faster aircraft like the U-2 spy plane could gather intelligence while remaining relatively safe from enemy interception. The B-36's reconnaissance variants were quickly superseded by more capable platforms. The political implications of bomber operations also became problematic. Flying nuclear-armed bombers near enemy territory was seen as provocative and potentially destabilizing. Missiles, stored in underground silos, were less visible and therefore less likely to provoke international incidents. The B-36's high profile made it a diplomatic liability as well as a military asset. By 1958, the writing was on the wall for the B-36 program. New bomber designs like the B-52 Stratofortress offered better performance with lower operating costs. The B-52 was faster, more reliable, and better suited to the changing requirements of nuclear warfare. Production of the B-36 had already ended, and retirement of existing aircraft was accelerated. The last operational B-36 mission was flown on February 12, 1959, marking the end of an era in strategic aviation. In less than 15 years, the B-36 had gone from being the most advanced strategic bomber in the world to being completely obsolete. The pace of technological change during the Cold War was so rapid that even revolutionary designs could become outdated within a decade. The retirement of the B-36 fleet was swift and decisive. Most aircraft were scrapped immediately, their aluminum recycled for other uses. A few were preserved as museum pieces, but the vast majority of these technological marvels were reduced to scrap metal within months of their retirement from service. The B-36's rapid obsolescence shows how quickly revolutionary technology can become outdated. In our current era of rapid technological change, are we seeing similar patterns? What technologies today might be the B-36s of tomorrow? Revolutionary now, but destined for quick obsolescence? Share your predictions in the comments. The story of the Convair B-36 Peacemaker ends not with a bang, but with the quiet hum of cutting torches and the crash of falling aluminum. By 1959, the last of these magnificent giants had been withdrawn from service. Their brief but spectacular careers ended by the relentless march of technological progress. But the legacy of the B-36 extends far beyond its operational service life. In many ways, the B-36 represents the end of an era, the last gasp of piston-engine aviation, and the final expression of World War II-era strategic bombing doctrine. It was the ultimate development of technologies that had their roots in the 1920s and 30s, pushed to their absolute limits by the demands of nuclear warfare and Cold War competition. The engineering lessons learned from the B-36 program were invaluable for future aircraft development. The challenges of building and operating such a massive aircraft pushed materials, science, aerodynamics, and systems integration to new levels. Many of the techniques developed for the B-36 were later applied to commercial aviation, helping to make possible the large passenger aircraft that followed. The B-36's hybrid propulsion system, while ultimately unsuccessful, provided important insights into the integration of different power plants. The lessons learned from combining piston and jet engines influenced later aircraft designs and helped engineers understand the complexities of mixed propulsion systems. Today's hybrid automotive technology owes a debt to these early aviation experiments. Perhaps most importantly, the B-36 demonstrated both the possibilities and the limitations of pushing technology to its absolute limits. The aircraft represented what could be achieved when cost was no object and engineering constraints were pushed aside in favor of performance requirements. But it also showed that technological excellence alone is not enough. Timing, strategic relevance, and economic viability are equally important. The human factors lessons from the B-36 program were equally valuable. The challenges of operating such a complex aircraft for extended periods highlighted the importance of crew training, fatigue management, and human-machine interface design. These lessons influenced the development of commercial aviation safety procedures and military training programs for decades to come. The B-36's role in Cold War strategy, while brief, was crucial during a critical period in world history. For nearly a decade, these aircraft served as America's primary nuclear deterrent, helping to maintain the balance of terror that prevented World War III. The psychological impact of knowing that hundreds of these aircraft were constantly ready to deliver nuclear destruction anywhere in the world cannot be underestimated. The rapid obsolescence of the B-36 also provided important lessons about the pace of technological change. In an era of accelerating innovation, even revolutionary technologies can become outdated within years rather than decades. This lesson became increasingly relevant as the pace of technological development continued to accelerate throughout the Cold War and beyond. The economic impact of the B-36 program was significant, both positive and negative. The program employed thousands of engineers, technicians, and production workers, contributing to the growth of the aerospace industry in California and Texas. But the enormous cost of the program, over $1 billion in 1950s money, also demonstrated the financial risks of pursuing cutting-edge military technology. The B-36's influence on popular culture was substantial. The aircraft appeared in numerous films, books, and television shows, becoming a symbol of American technological prowess and Cold War tensions. Its distinctive appearance and massive size captured the public imagination in a way that few military aircraft have before or since. From a strategic perspective, the B-36 represented a transitional technology, a bridge between the conventional warfare of World War II and the nuclear warfare of the Cold War. It was designed for a world that was rapidly changing, and by the time it entered service, that world had already moved on to new challenges and new solutions. The environmental impact of the B-36, while not a major consideration at the time, was significant. The aircraft's massive fuel consumption contributed to air pollution, while its noise levels were so extreme that they caused property damage and hearing loss among ground personnel. These issues foreshadowed later concerns about the environmental impact of aviation. The B-36 program also highlighted the challenges of managing large-scale technological projects. The complexity of coordinating thousands of suppliers, managing changing requirements, and integrating new technologies provided lessons that influenced later aerospace programs. The program management techniques developed for the B-36 became standard practice in the aerospace industry. The international implications of the B-36 were far-reaching. The aircraft's capability to deliver nuclear weapons anywhere in the world fundamentally changed international relations and military strategy. Other nations were forced to develop countermeasures, leading to an arms race in air defense systems and strategic weapons that continued for decades. The preservation of B-36 aircraft in museums around the world ensures that future generations can appreciate the engineering achievement that these aircraft represented. The few surviving examples serve as monuments to the ambition and ingenuity of their creators, and as reminders of a time when technological limits were pushed aside in pursuit of strategic advantage. The B-36's influence on subsequent aircraft design can be seen in many later programs. The emphasis on long range and heavy payload capacity influenced the design of the B-52 Stratofortress, which remained in service for over 60 years. The lessons learned from the B-36's defensive systems influenced the design of later bombers and transport aircraft. Perhaps the most important legacy of the B-36 is what it teaches us about the nature of technological progress. The aircraft represents a perfect example of how revolutionary technologies can become obsolete, not because they fail to work, but because the world changes around them. The B-36 was a magnificent solution to a problem that was rapidly becoming irrelevant. In today's world of rapid technological change, the lessons of the B-36 are more relevant than ever. As we develop artificial intelligence, quantum computing, and other revolutionary technologies, we must remember that technological capability alone is not enough. Success requires not just engineering excellence, but also strategic relevance, economic viability, and perfect timing. The story of the B-36 also reminds us of the human cost of technological ambition. The engineers, pilots, and crew members who worked on this program sacrificed years of their lives in pursuit of a goal that ultimately proved ephemeral. Their dedication and skill deserve recognition, even if their creation was destined for a brief operational life. As we face new technological challenges in the 21st century, from climate change to space exploration to artificial intelligence, the B-36's story provides both inspiration and caution. It shows us what can be achieved when human ingenuity is unleashed and resources are unlimited. But it also reminds us that even the most impressive technological achievements are subject to the relentless forces of change and progress. The Convair B-36 Peacemaker was many things: a triumph of engineering, a symbol of American power, a bridge between technological eras, and ultimately a magnificent failure. It represents the best and worst of human technological ambition. The incredible things we can achieve when we push the limits of what's possible, and the humbling reality that progress waits for no one, no matter how impressive their achievements. The B-36's legacy reminds us that, in technology, as in life, timing is everything. What modern technologies do you think might follow the B-36's path? Revolutionary today, but potentially obsolete tomorrow. And what can we learn from this aluminum giant about balancing ambition with practicality? I'd love to hear your thoughts on how the lessons of the B-36 apply to today's technological challenges. Thank you for joining me on this journey through the remarkable story of the Convair B-36 Peacemaker. If you enjoyed this deep dive into aviation history, make sure to subscribe to Never Built for more stories of ambitious technologies that change the world, even in failure. And remember, sometimes the most important lessons come not from our successes, but from our magnificent attempts to achieve the impossible. Until next time, keep looking up at the sky and wondering what might have been.